So guys, in this video, I'm just gonna highlight the evolution of how the data center access layer design, access slash distribution layer design has evolved. So in evolution of data center access design. So if you go back 20 years, your data center looked like something like this. So you had a host, a server basically, that's running the applications, whether bare metal or virtualized. For redundancy purposes, he would connect to access layers, access layer switches in a redundant fashion. Now here, obviously, one is active and the other one is standby. The NIC actually, the physical NIC, the cables connecting to the access switches are in active standby. Okay. So this guy is blocking or standing by, but it's configured in the host with the same IP and the same VLAN. So that if this switch goes bad, or this cable goes bad, or this NIC goes bad, you have a redundant NIC, redundant cable, or redundant switch to have your operations take over from that perspective. So now the access switch was L2, layer 2 purely. Now the distribution switch is L3. This is where your IGP is running, like OSPF most likely, or EIGRP. Back in the days. And this is where your HSRP is running, hot standby router protocol, which is basically doing a virtual IP for the default gateway. The default gateway sits here. He's got a default gateway. Let's just say is equal to 10.1.1.1. So this virtual IP would be 10.1.1.1. But in actuality, the physical interfaces with HSRP would be 10.1.1.2 and 10.1.1.3. So one would be a virtual IP, and their MAC address would be different. He's going to be at MAC 1, he's going to be at MAC 2, but they're going to be, basically sharing this IP to resolve. 10.1.1 would be resolving to either MAC 2 or MAC 1. So that's how your HSRP worked. It's sending hellos back and forth to make sure that both the switches are up. If anyone goes up, down, it will take over. So let's say this one is active, this one is standby, and the access switches would connect in a cross fashion. And obviously this would be a STP based topology spanning tree protocol where you have a loop. So you would block your standby for that VLAN. So this active L3 switch would also become, so it's an from an STP perspective, this would be your route for the VLANs that this is active, and it is also active for HSRP. So two protocols at least that are bound to be converged when a failure happens. At least that's number one is STP, then number two is HSRP. They need to converge. Now they won't be converging in sync because there's no link between them. They will converge at their sweet time, but both have to converge for a failover to happen. So you got two protocols that are in question here, where if anything goes wrong and it needs to converge to this standby, HSRP needs to become active here, STP needs to become root here, and then so on and so forth. And then your IGP, OSPF, or EIGRP would be at, talking routing here. Above to your core. So this is your traditional 20 years ago design, host connected with an active NIC and a standby NIC. Now, I have to erase this because I don't have enough space here. So IGP, OSPF, EIGRP. So the next evolution from primarily Cisco, and this was like a Cisco out-of-the-book design that the industry followed. And the next step in this was the Nexus. This is like the non-Nexus design, which was CAT 6Ks or 5Ks for that matter, wherever you want to use it. 5Ks here and 6Ks here. That's a Catalyst STP based, STP HSRP based design. So now came two designs. Evolution is happening now, and then now Cisco comes out with, okay, my access layer is going to be 2K, Nexus 2K. Now this is Nexus based. Two Ks that connects to 5Ks, Nexus 5Ks. And the biggest thing here is now that your host is in active state. So now you created a port channel here, and both of them are active. And the 2Ks are pure L2 devices, just like in here, in this design, but they also cross connect here with a port channel. And this one, this link is also a port channel, but it's called a virtual port channel. What is that? Basically gives the L2 switch the ability to look at the L3 switch here as one switch. So virtually this guy is actually having a port channel to one switch, logically one switch. That's what VPC was. It still ran STP in the background, but did not block because it was communicating between each other. The L3 switches were communicating with each other on the VPC link. So they won't let the packet go in loops. So this guy sees the uplink as one switch. The host sees the L2 switch as one switch because it's port channel. Port channel typically goes one device to one device, but here we have two devices and we don't have anything connected to them, but the actual connection is VPC. It's a very, very ingenious design to enhance your bandwidth and your failover rate, resiliency, redundancy for this host. And you're still running HSRP here on a separate link. You're running HSRP exactly like that. So, but the biggest part that changed in this from Catalyst to Nexus was the port channeling and VPC. Very, very awesome design. STP was still in the picture and just running in the background. So that's, and then again, your HSRP and L3 where your IGP is talking to the core right here. Core firewall or whatever you want, routing. So that's your Catalyst to Nexus with port channeling design. And now came the next step in this evolution, which is called the spine leaf. Spine leaf. So the spine leaf is where you're completely eliminating your spanning tree. And how is that happening? So here's your layer 2 access switch, not layer 2, but your access switch, access layer switches becomes, instead of L2, they become L3. And then your distribution stays L3 as well. But then your question becomes, how do you trunk? Because here you're trunking. This is your trunk. Your VLANs are trunking. So in spine leaf, you are transporting your VLANs over VXLANs. So basically, now you're encapsulating L2 into L3 IP packet, and you don't need trunking anymore. No more trunking. So this is again trunk-based, trunk-based. Trunk is again 2 or more VLANs traversing these links are trunks. So you have obviously not one host on one VLAN, but you got multiple hundreds of hosts connecting on different VLANs. So everything needs to be trunked here. So these links are trunks, trunks. So this is like a trunk free. This is also trunk, more than 2 VLANs traversing everything here. This is a trunk free because now you're doing transport of VLAN in encapsulation mode, VXLANs, and this is your L3. So your first hop, now your host, is connected like this in a port channel fashion again. You do have MLAG, but you do not have HSRP. But what you have here is Anycast gateways. So you got Anycast means your default gateway here is 10.1.1.1. So your Anycast is 10.1.1 here, 10.1.1 here. And if it goes down, your VARP, virtual ARP, is going to respond to the request from the host for the MAC address by this link here. So this is your spine leaf evolution, which gives you the ability to go not only like this, but multiple uplinks, scaling the bandwidth not only from 2, but you can go like 3 like this if you want to scale. And these topologies you can't really scale. You have to stick to 2, a block of 2 switches, and that's about it. In spine leaf, you can go horizontal scaling like this, where your access leaf now can go as many L3 distribution switches as possible. So that's basically a high level of evolution of how the data center topology has evolved from spanning tree to non STP, non HSRP based topology. I've got a video on this on spine leaf. You can take a look at it to see how that compares the traditional versus spine leaf. Hope this helps.